in collaboration with Ilya, Francesco, and Alessandro. Okay, so let's go through. So let's start with the motivation. Why should we care? We read a big, so maybe people will see also. I think so. The motivation, why should we talk about thermal correlators? First of all, so I guess I'm interested in thermal correlators in general because they can give you some kind of more info on CFT data. And the CFT data I'm talking about are the usual ones. So I'm just talking about scale and dimension of big coefficients. Okay, so why should we care about them? Because the difference with respect to zero temperature, there's going to be some kind of repackaging of the CFT data into these correlators. And this might lead to new insight or new constraints on your theories. The most famous example is probably in 2 dimensions. So in 2 dimensions where you can put your CFT, final temperature means it's equivalent. So phi final T, temperature is going to be equivalent to putting your CFT on a torus, so on S1 times S1. And okay, the most famous example people might be familiar with is the Gatti's formula, where you can get some constraints on the limit of delta going to infinity, which is going to be what also we're interested in. But also there have been lots of other works in this, in this case, like one of the recent one I'm going to mention is, for instance, the one by Collier, Maloney, Maxfield, and Ziares in 2020, where they also gonna bound OP coefficients and other things in 2 dimensions in this limit. But okay, if you're familiar with this work in 2 dimensions, one of the key ingredients has been really modular symmetry. So they really use the heavily rely on modular symmetry. And if it's not clear what's going to happen in higher dimensions, modular symmetry. So we're not going to use or talk about modular symmetry in this talk. And so what we can do, what about now? How can we get bounds with this kind of objects in the quasi-gradient trip? And it's going to be the topic of our talk. So we're going to stick to these dimensions. So if we're talking about thermal correlator, the first object to take a look at is going to be the partition function. And from the partition function, one can see the spectrum in general. Spectrum. This is something which is familiar to people since lots of time, but it has been more systematized in a recent paper by Benjamin, Lee, Oguri, and Simon Staffin in 2023. And okay, the next object to look at the partition function is going to be, you can imagine the one-point function and zero temperature. And CFT data that you can read from this one-point function, okay, we'll define this object much better later, so don't worry if you're not familiar, but there's going to be OP coefficients. And the form of the OP coefficient is going to be the following one. So the OP coefficient where you have the external field, and then you have 2 internal fields, which are going to be equal because there's going to be in the thermal trace. And the goal of this talk is going to be to learn something about their delta going to infinity limit. And it's going to be something, and for these things, it's going to be something new in this regime. And here we developed a bit more what was already known. Okay, so these are kind of the motivations. Let's just go with the outline at the top. So we'll try to define you the objects. Then we'll define the blocks, the conformal blocks we're talking about. Through orthogonality, we'll get an inversion formula, and then we'll show you how to get this limit, first in an example of free theory, and then in some more general case. Yep. Yeah.
Always the name is DFT, partition function is finite, or U is finite, and then from the you derive constraint. So like what is the assumption?
Yeah, I guess. Yeah, I guess I'm assuming finiteness of the partition.
It's always the case.
What, sorry?
Is it always that it should be the case?
On the T minus. You have spectrum which is lower bounded. You have a spectrum which is lower bounded from below. Why not that? Every state is you can write down summation e power minus beta delta.
Yeah, but it depends on how fast the density of the state grows.
Well, one of the prediction of this thing that, like, if you take beta going to 0 limit, you can write down from effective theory on SD minus 1, assuming there is no gapless mode when you do the reduction. And once you assume that, then this EFT predicts something, and you can figure out how the growth of density is, and then you can show that.
It's a bit sort of logic to use.
Yeah, I guess the point is that once you do the reduction, and if you assume that the CFT is valid, then the finiteness is correct. I mean, if you want to spoil the finiteness, then you have to do something very drastic. For example, say that energy density at high temperature is not extinguished, and things like that.
Yeah, I guess I don't have any proof about that. We're gonna work where we can do this. I don't know any also counterexample. So I don't know. I think the example in free theory, everything is working quite well. And then we're gonna use this 3D assumption. So apart from that, yeah, I don't know precisely. Okay, so let's talk about the definitions of what we're talking about. Okay, so I will define the endpoint function at finite temperature, where I call beta and mu as the trace over your Hilbert space of your fields x1, phi n, xn, with the insertion of the dilatation operator, and then you have some other operator. Okay, beta is as usual the inverse of the temperature, and these mu are chemical potentials, and these H1, HR, okay, or N, are cartons of SLD of the rotation, cartons of SLD. And you can see that in 2 or 3 dimensions, you're going to have only one cartan generator. And so you can see this is the standard action, that is the standard definition that you also have on the torus in 2 dimensions. You already see that you have less symmetry with respect to the correlator at 0 temperature because you have the insertion of these extra things. And so you're going to have less worded entities. So you're going to have only worded entities from the dilatation and the cartans. And this is the first implication is that your one-point function of finite temperature and chemical potential is different from 0. So this is the first difference. Let me do now a remark about what is known in what is called in literature thermal correlators. Most of the times, people are going to refer to a CFT put on a different manifold, which is the following: S1 times RD minus 1. Instead, what we're talking here about is the most general case of S1 times SD minus 1. And you see that this is in 2 dimensions again. In 2 dimensions, this is just S1 times S1, so just the torus. And okay, these 2 topics are related. That's why people are calling both of them thermal correlators. And the way you should think about is that this is really the T going to infinity limit of this other manifold. And this is not a straightforward limit, but that's more or less the idea. And you can see the first difference is going to be that the one-point function in this geometry is going to be non-zero, but it's going to be fixed apart from some dynamical constant. Instead here, it's going to be non-fixed. And this is going to be the object we're going to study. And you see here, we're going to have the usual CFT data, like delta and OP coefficient. Instead here, we're going to have some kind of repackaging of CFT data into this like dynamical coefficient P. Okay? Once you have this, your definition, we can go to the next step. And we can start talking about blocks. Because this one-point function, so phi of mu, beta, mu, allows for a block decomposition. Block decomposition. And the way to do it, okay, so first of all, we're going to stick to 3 dimensions from now on. And this is important because you see in higher dimensions, you're going to have a different number of cartons generator, and the study is going to get more complicated on a technical level of speaking because we're going to have more variables. But okay, so from now on, we're going to stick to 3 dimensions. And okay, and this one was first done in a paper by Cobain, Maloney, and DMV in 2018. Okay. Okay, then the definition of blocks is the usual one. So we're just inserting a projector on your primary operators in your 1-point function. And then let me just define this other quantity. Now we're sticking to 3D. I'm calling Q as e to the minus beta, and y is going to be e to the I mu your rotation, and y mu. And here you have your rotation of your Cardano. And okay, now you use the Dolan and Osborne approach, which is going to give you the Casimir operator. And the Casimir operator is some second-order differential equation in our variable, which now are going to be so Q, Y, and S, where S is the cross ratio made of our space-time variables of the X.
Could you try different?
Yeah, you could try different. I mean, it's going to change the. Sorry. So I can do both. Okay, let's go in the other board. Okay, now once we have the Casimir, we can try to get the blocks. As usual, it's difficult, so you don't have a full control over them. It's going to be even more complicated than the 4-point function zero temperature case, because you see now, I mean, you don't have just 2 variables at the bar, but you have 3 variables, so it's even more complicated. So, okay, so how do you do this? You get the solutions. Okay, this is better. Yeah. Solutions with a couple of expansions. So the first expansion is going to be the small q limit, small q expansion, which means small temperature. Okay, and this is, so our block, we're going to call it with this. So you have the quantum number of the external operator, then you have the quantum number of the internal operator, and then you have an extra index, which is counting the tensor structures. Okay, and you can do, so the first thing at small temperature is going to be some expansion. You have some number depending on your quantum numbers, and then you're going to have Q and 1, Y and 2, S and 3. Where N2 and N3 are going to be bounded at N1. So you do an ansatz, then you act with the Casimir, you can get some regression relations, and you can get these numbers with the regression relations and the blocks. This is exactly, if people are familiar with the zero temperature case, this is more or less the same way. And you can go pretty high values of delta here. The other expansion that we will need is going to be the large, where am I? Okay. The large delta expansion. In the same way, so we'll write the block. Now it's going to be some sum of an n from 0 of a function of q, y, and s, delta to the minus n, where the delta is the internal delta, so this one. Okay, now here we have some system of linear equations, so it was much faster. Here to get instead this coefficient, it's a bit harder. You can always get them iteratively, but now you have to solve one integral each step, so it's a bit slower, but still doable. For instance, okay, let me just say that the zero term is going to be equal to just the conformal character at zero delta. It's just conformal character. And okay, so these things are doable. This one a bit slow, but yeah, you can compute them. And now we can go to the next step. So everything is fine. So it's going to be the inversion formula. Okay. What are we going to do here? Now the strategy is that we have a Casimir differential equation. We have our blocks in some limits. Now we want to understand the orthogonality of these blocks. The way we do it, so we're going to ask the Casimir, since we are differential equations, to be asymmetric operators. And this is going to give us the measure, so measure V mu S. And once we have this, we can write what is the orthogonality for these blocks. The orthogonality is going to be the following. So you have an integration in the beta, you have an integration in the mu, integration in S, Then you have your measure. And then you have your two blocks, where one is going to be the shadow with both internal and external dimension. Just remind you that the shadow is defined as T minus delta. The definition, and this is going to give you a delta function in the spin, in the dimension, and with a suitable choice of tensor structures, also going to be also a delta function in the space of tensor structure, A1, A2. Okay, the easy way to also understand this orthogonality and just check it might be with just the conformal characters. So I mean, if you can also just get from the Casimir the characters, and then you know them explicitly, not just with an expansion, and you can just use the orthogonality to see that you have at least this part of the orthogonality. Instead, for the blocks, it's a bit more involved, and also you have to choose smartly a basis to have these, but you can play exactly the same game. Okay. Now that you have the orthogonality, you can go to the next step. So the next step is going to be inversion formula now. Okay, I will write down the one for the. So if you now you can write just from a general point of view, you can write the normalized one-point function, and you can say, okay, just from conformal symmetry, you should be able to write this as a decomposing as a sum over conformal blocks. So let me see.
Is this orthogonality relation still true when delta is not on the principal series?
Okay, this is with data not in the principal series. If you have data on the principal series, you're going to have another kind of orthogonal relations. This is the same with characters. So, and this is going to be beta more or less. So if you have beta real, you're going to have the data on the principal series. Instead, if you're not going to have data on the principal series, you're going to have beta complex if you want the orthogonality. This is, I don't know, the nicest way to see is from the characters. Really. There you just see that you need the complex case or not complex case, and you can go around with that. Sorry.
Is the delta function?
The delta function A is going to be in this other quantum number, which is the label for tensor structures. So, I mean, you see here, since I was telling you that these things are, the one-point function is going to be more or less, let me just say this, maybe going to be something like, you can think of them as a sum over O by O, and you see that here we're summing over O in the inverse space, so these objects are going to be genetically spinning, even if here we put a scalar, and so we're going to have lots of tensor structures, and so this index is going to count the tensor structures. Then if you want to have this orthogonality with this measure, you have to be smart and pick a smart choice. So yeah, this was some part of technical details, but which is pretty important. Okay, so I was saying here you can decompose your one-point function. So you're gonna have an integral in the dimension, a sum over L. Then this is gonna be your spectral density. Then you're gonna have a sum over your tensor structures, and here I'm gonna define the object we're going to be talking also later. This is so the density of OP coefficient. And then we're gonna have our block. Phi, A, delta L. Okay, from now on, we did everything for phi scalar for these computations. I forgot to tell you this, sorry. But in general, we have the blocks also for external spinning operators. So in principle, one should be able to repeat the same story also for spinning external. And okay, so from this, you can just use your orthogonality to invert this formula and get your density of OP coefficient. So rho delta L, and then integration with beta d mu. Yes, where this is just that integration over there. Your measure, then you have your partition function and your one-point function. Okay, and this is going to be the main formula we're going to use for our explicit computations. And the way you do also for the spectral, you can do also the same game for the spectral density. where you're just going to use the inversion with the characters. So it's more or less the same formula. Okay, you can write it down just for a sake of time, but you can do more or less the same.
There is also the block.
I forgot the block. Yeah, thank you. So you have the block.
So this is a Euclidean inversion formula.
This is, I would say, not Euclidean because, I mean, you're in the Euclidean space, yeah. I mean, X is Euclidean, but okay, but the delta is not in the principal series, but it's the real delta.
Okay, but it's not the kind of thing that could determine the whole one-point function from like an absorptive part.
Yeah, no, it's not. That's sorry. Okay, so now let's go to the example. So let's go to free theory. And we want to use this formula. Okay, the first thing to do is to just use the one for the spectral density, so the easier one. So you can just say from combinatorics, in free theory, you can write your partition function explicitly as some product formula. Sorry. Phi delta m, you can write very explicitly as 1 minus q to the delta y to the m. Okay, and this one, you just know from the conformal symmetry, this has to be equal to some decomposition into characters. Let's say m delta n, pure characters. Okay, so from just this first step, you can see that just by expanding left and right, you can read these objects, which are going to be the multiplicity. So just your spectrum in from the lowest delta, from the lowest dimensions. So then what do we need? Okay. Then what do we need? Then we need this object, the high temperature expansion, IT expansion, and this is going to be the limit where we will be work on. So it's going to be beta going to 0 and mu over beta fixed. And this object we're going to define called as capital omega. Okay, this is not the only limit that you can study. There was also you can also study the mu fixed limit, and this was done, for instance, in a paper by Benjamin, Lee, Sridip, Simons Duffin, and Ishin in 2024.
Can I ask, why is this particularly interesting to do fixed ratio?
I mean, for us, it was more of a how to get the bounds. I mean, like it was a way to get, you see, to use this format to get a sort of point approximation. So, I mean, it would be interesting also to study other limits. Like, okay, this one was already done in the paper by Sridip, but I guess in principle, if you're able to do also other things, that would be nice.
Also, the behavior is super large. If it's not the limit, it's not. You just limit concepts.
Yeah, I guess this is the easiest one for to study for now. And okay, the way you get these from your partition function in free theory is from some Mann transformation. You can just write the expansion in the small temperature limit. I will just write the first term very quickly, just to show you that we can do it very explicitly. So this is going to be some Riemann zeta function, and then you have omega squared plus a log beta term times 1 plus 2 the square over 1 plus 1 squared plus corrections. Okay, now, and from this you can read one interesting quantity that can be the free energy density. Density, which we'll call F, which in free theory is just zeta 3 to pi. Okay, so from now you can just take our inversion formula. We plug in, okay, for the spectral density, sorry, it's not written down, but you can imagine that. Then we plug in the high temperature limit of the partition function. We have the knowledge of the characters, and we can just do a certain point approximation from the inversion formula. And we get our first high delta limit of the spectral density, which is going to be some number, some spin dependence, the free energy density to some power and some scaling in delta. So sugar 3 will be 1 plus corrections. Okay. So what can we do now? We want to check how good this approximation is with respect to the exact values.
And then exponential.
Any exponential?
This is the density of states here.
Yeah.
Yeah, the yeah, somewhere exponential.
There should be some exponential. You need a, yeah, some not right.
Is this
Okay.
I think the dependence will be exponential. That will be
Yes, here. Okay. Yeah, already done that on my notes. Okay.
no, sorry, this. Maybe the power is on also. But anyway, there is a formula.
In 3 dimensions, that's power, right?
But why there is a 3/36 sitting there? No, that's not in the exponential. They're gonna look it up in the back.
Okay.
Yeah,
Sorry,
yeah.
guys. Okay. I'm sorry, guys, for this. Okay. We have a formula. Yeah.
No, I think the E was right.
D was right.
He was right.
Yeah,
but the-
okay.
Then the power of delta is wrong.
Maybe the whole thing times delta to the.
The 1 to 1/36 goes in front.
Yeah, it should be somewhere else. Yeah. And
That's the hash code.
okay, but anyway, let's compare this with data. So we can extract the multiplicities from here, from high values of delta, and we can compare with our asymptotics, and it's going to be our next plot. So the plot, the n is going to be the exact data, and this is the ratio over the asymptotic values. And okay, you see, the leading term is not even in the plot because it's very off. It's 40% off with respect up to these 200 values of delta. And then you see that you really need to do some leading terms. And if you do this, you actually get a very good match with your exact data, already at very small delta. So the first take-home message from these plots, from the spectral density, is that if you want a good match at finite delta, you really need to go to some leading terms to compare with your exact data.
What is n over there?
N is the exact multiplicity, what I call them, sorry.
Oh.
So I got them there, and then rho is going to be my spectral density. So that's a log. So when it's going to go the closer to 0 it is, the best the approximation is.
But how many universal this point?
No, this is not universal. This is free theory.
No, I mean the one this.
This one, yeah, this is still free theory because we're putting the log of zeta coming from free theory. Then the rest is just block decomposition. So my inversion formula here, this is universal. Like the block part is universal, everything else is universal apart from, for now, z and the 1-point function. Then I will show you that if you do some argument and you put some z and phi, then it's going to be universal. But for now, I just put the one of free theory, so I'm getting the result for free theory.
When you switch to free theory.
Sorry?
When did you switch to free theory?
Here. Yeah. Here I switch to free theories, and everything now is free theory, just an example to show you how it works, and also some nice feature that you really want to do in higher, like in some higher order. Okay, but for now, this is it. This is good here. The just next step for free theory, then I'm going to the general case, is going to be, you just repeat the same game also for the 1-point function from the inversion formula. Now you have the spectral density.
Still 5 minutes, right?
What? Yeah,
5 minutes.
5 minutes, yeah. Yeah. I'm gonna do. So let's hope now that, sorry. That I have the correct formula written down. So you can just write down the OP density. Okay, so this is going to be the OP density, which is coming from the inversion formula and then the saddle point approximation. And again, we can play the same game with the exact data. And I'm going to show you some plots. So these are just an example of exact data for internal spin 2. And you see different colors are going to be different tensor structures. And you can see some feature that is also going to show here, which is the fact that when you more tensor structures, they're going to be much more suppressed. if you change the index A. And then if you want to compare with the plots, again, you see exactly the same behavior. So if you just put let's say the leading term, this is quite out with the data. But then if you also add corrections, this is gonna improve much more, and it's gonna be on top of the data. This is for the spin 0, but you also see the same for the spinning operators. Since for the A=0 case, they're not spin dependent, you're gonna see different optic coefficient, different spins, and they're more or less all on top of data. Okay, so I hope that I pretty much convinced you that this is working, and this is working pretty well, but also the fact that corrections are interesting. And I'm gonna do now the general case. So the general case, generalizations. You see that the only input that we need to get to our formula was the high temperature behavior of the partition function and of the one-point function. So if we have this, we can play exactly the same game as we did in free theory and get to some result. Okay, this is what we're gonna do. And so the way we're gonna do this is gonna by using this thermal effective field theory plus some structure of the blocks. Gonna be clearer a bit now, where you can write, let's say, an ansatz for your one-point function coming from these things, which is gonna be the following behavior in beta. 0 plus 1 plus lambda squared. Okay, so we have the behavior in beta coming from the thermal effective field theory, and you can recognize the first term as the one coming from the S times RD minus 1 limit of the one-point function. And then you can have the behavior in S and omega squared coming from the structure of the blocks. Once we have this, we can go to our final formula. So that's what I'm going to write down, where you can compute both the spectral density and the optic coefficient density with also subleading corrections. And in this general case, we're going to have 3 0 plus corrections. Okay, so you see a very similar structure with respect to the formula in free theory. You see that here you have the same damping factor with respect to the tensor structures. And the main difference is going to be with respect to the other formula, this behavior of delta pi over 3 of the scaling in delta. Okay, this one we can also check from, because it's the same as found in a paper by De La Cretas in 2020. And he was computing this by assuming eigenstate internalization hypothesis, which we were not doing. So this is something that it's a nice match. And you see that the first dependence in the leading term is going to just come from this B0 factor, which is the one which is regulating the one-point function in this limit. And so, but we can also compute the subleading correction of this object, and the subleading correction will also depend on these other coefficients. Okay, now I'm going to quickly conclude. Okay, so just a brief summary. So with the one-point function, we can get the Casimir equation, we get the blocks, then we got an inversion formula, and then from an inversion formula, we can use it using also some thermal EFT structure of the blocks to get some handle of the one-point function in the high temperature limit, which should be universal with some assumptions. And from this, we can really get through some point approximation our main results, which are this OP density. Okay, just for the future, it might be interesting to study other theories now that we have this machinery. Other theories, for instance, we can start going like GFF or some holographic theories to see what's going to be the behavior. Okay, so a more long-term goal might be what's going to happen if you study constraints of a higher point function, always at 0 temperature, higher point function. And with this, I'm done. Thank you a lot. Yeah.
So it's kind of 3D, right? So they give the jam theory.
Okay.
So they can give them a big solution. That still stays growth after the next connection. So what of that plot?
What of the plot? Okay, so
You can take deep infinity just that makes sense.
yeah, I guess so. I think the problem is going to be here in the assumption. So here we're using this thermal EFT to say something about very general. I guess in some cases, this thermal EFT you cannot use, like also for free theory, it's not the same behavior. So I guess if you
But then something, it's just check exists satisfied, and then you can define keep doing the initial limit of safety.
no, I mean it's general in the sense that if these things applies, then you're gonna have a result. If these assumptions are gonna be like probably your theory is not gonna be true, I don't know. Then you cannot, of course, do the machinery. You have to do something else. But if you have on your theory a control over the one-point function or the partition function, then you can do exactly the same game. So this is just let's say this is an ansatz. If you have another way to get this one-point function, you can just apply the machinery and get your result. So if in your favorite theory you have an handle over the partition function, you can just play this game. If it's convergent, of course. If it's not, yeah, okay.
My favorite is the
Okay. Well, sorry.
in my favorite theory the
Okay.
I think the only examples where you think it will fail are either free theories where you can modify it or systematic type of small, which is unfortunate theory example.
I can break the pessimistic risk.
Then should probably work. Great lesson.
We're still figuring out better with my work.
But it's open, it'll still be planar.
Yeah, it's still like a plane. That wasn't your list.
Maybe I think.
Yes.
Could you give a sense of what these corrections look like, so I know that I can't take delta to be a order and delta 5?
Well, sorry, you're saying this correction or this correction?
Is correct.
This one? What do you want to know? The numbers or what?
Oh, no, just like with the, I mean, because this is like a heavy light.
Yeah.
Asymptotic, so.
Yeah.
I shouldn't be able to take delta 5 and be in the same order as delta.
Yeah, you should not. Yeah.
So I guess how badly does it break?
I guess the delta phi dependence is mostly from here. You have this kind of behavior in delta phi, and then you're gonna have some polynomial dependence over delta phi here inside. I don't know if this is gonna be. I mean, you're asking how these things are gonna depend on delta phi, right?
Sure, I mean, there should be a pattern of delta there should be some patterns of delta 5 there, just.
Yeah, there's gonna be some factor of delta phi in some polynomial way. And yeah, of course, you're thinking about delta phi finite. This is your limit.
Sure, okay.
I don't know.
I think if you find the saddle,
Yeah,
the saddle will depend on delta phi. And you want this saddle to be very close to 0 beta. And that will some condition, some estimates. Or delta phi should be here with it. And the series is the power to look up to move that.
Yeah, I think we don't have anything like precise. Yeah, precise argument, but I guess.
yeah, if you're doing a saddle, maybe you could do a one determinant.
Sure. I mean, yeah, we computed the corrections. Yeah, we know.
Oh, okay.
We have the corrections, but that's final delta. This was one of our assumptions. Yeah.
Also, how different is this ETH thing? I would have thought this ETH is also basically saying that the one-point function in some heavy state is same as thermal one-point function, which is basically what we are doing.
Yeah.
So it's not an independent check. That's what I'm saying.
It's not an independent check. Why? I mean, okay, the way they're computing this is completely different. Some completely different ways.
His point is, he's assuming.
So I am saying that assuming ETH is kind of a stronger. So what you are doing is, roughly speaking, you are saying the canonical ensemble is same as microcanonical.
Okay.
And then this statement, this OP coefficient is in microcanonical ensemble, and there is some assumption on how you average over. And that is same as the canonical ensemble answer, which is the one-point function you compute with this partition function.
Okay.
And ETH is a stronger version of the statement where you basically make the window very small.
Yeah, agree.
So in that sense, philosophically, it's the same kind of computation. Well, I don't know what to look at it in that paper, but
Yeah, I guess his assumption is stronger. That was my point. Like,
Yeah.
he's doing a stronger assumption, which is fine. And also he doesn't have all the corrections. So in some sense, we're doing some more. So we're assuming less than him, and we also have more control over this data. Of course, he's doing also other things in the paper. So
Yeah.
it's not because of that. I was just saying that as just a check.
Also, we don't assume that it's some errors. Well, you don't assume because you hide all the things in the averaging process. Thank you. So there is averaging process is being done somewhere in the game. It's not a true answer.
But it's literally the sum of primaries that have put at the generator. So you just get a-
Just that. Wait, it is a continuous function, but on the other side, we know this is not a continuous function. It has to be supported, like all this stuff, everything should come at some.
Yes, this is the result for a CFT on S1 cross SD minus 1. So it's thermal by definition in your case. You don't have to, you're not computing some other observable and then assuming it's equivalent to a thermal calculation. Is that what you're saying?
Yeah, well, all I'm saying that essentially when people say ETH is the stronger version of ensemble equivalence, where it says that canonical ensemble result is same as microcanonical.
Yeah.
But the microcanonical window is very, very small. And here I think is effectively similar.
That just means that this integral can be done by a certain point approximation.
Yeah.
But here we don't assume, I mean, we just do the integral, I mean.
Yeah, of course.
So we don't, you don't need to assume.
Yeah, I agree, you don't assume ETH, but then, I'm trying to say that these two are kind of philosophically same. Like, in the sense you take the answer from the canonical ensemble and invert it.
Any more questions? Yes, thank Francesco.
Where are you?
I was reading for you, John.
Good job.